Hey everyone, and welcome back. This is vsCTF 2023, a CTF hosted by ViewSource. Overall, a lot of fun. I focus mostly on Pwn challenges, but I'll be covering 7 challenges in total. The timestamp should be below. The CTF hasn't ended yet, so I haven't seen anyone else's write-ups, but if there's an easier way to solve any of them, I'd love to know. And with that, let's get started. This is Pwn RPS by Wrench. It says, just a classic game of rambunctious parchment snipers. We're given a netcat port and a download file. So for this, there's only one download file. It's just the RPS binary, rock, paper, scissors. In the binary, there is a win function. So we can see if we can call this function, we get the flag. And if you go through the code for main, you'll see that it'll actually call the win function for us if we can beat the computer in like 30 or 60 games of rock, paper, scissors. So 50 games of rock, paper, scissors, then it'll give us the flag. So not too bad. And I think this is a kind of traditional challenge. What's going to happen is that the process is going to read from dev-urandom. Then it's going to use that to seed random. And then from there, somehow we need to leak that random seed key. And if we can, basically it's going to play rock, paper, scissors, 50 times. And the computer is going to choose, or the remote process is just going to call rand, 50 times. And as long as we know what that rand is, we can win. And the trick for actually beating the computer or determining that seed that they're going to use is there's a printf vulnerability here on our name. What we can do is we can exploit this printf vulnerability to leak the seed that they're using for random. And so then we know when they do rock, paper, scissors, we know what choice they're going to choose, and we can just send the beating or the winning hand. And if we do that 50 times, we get the flag. This is what it looks like in the solve script. This is just generic stuff. We're going to connect to the remote host. First thing first, you need to open up GDB or something and figure out what seed they're using. So I just go through like this. You do 1, then 2, then 3, then 4 until you find the one that's the seed that they're using. I think for me it was 9. Oops. 9. So the 9th value on the stack is the seed for rand. So once we have that, we'll copy that out, and we're going to use the ctypes library from Python to load in libc so that we can use the libc version of srand and rand. The rand on Python is not the same as the rand on C. So you just need to make sure you're using C's rand. From there, once we know what the remote process is going to pick, it's pretty simple. We're just going to take their rand, figure what it out. And so if their rand is a 0, we're going to send paper. If it's a 1, we're going to send scissors. And if it's 2, we're going to send rock. We do that 50 times, and after that we get the flag. So really not too bad. So we can do Python 3, solve.py. Make Ubuntu 22, Python 3, solve.py. We're sending all of our hands, and cool, we get the flag. And it says, what the heck, bro? Guess God knows all my moves, sad face. So, pretty fun. Next is Pwn Tiny-Pwn by Wrench. It says, recently the GOAT univariant taught me how to elf golf. I was so proud of what I made, I wanted to show the whole world. But go easy on him, he's just a child. We're given a netcat port and a download file. In the download file, there's only one file. It's called Tiny-Pwn, and it's a very small 32-bit executable. If we open it up in Ghidra, this is all the code right here. It's very small. And what this code is going to do is it's going to set up for the syscall read. It's going to read in OXD bytes. It's going to set that read into, or send it to the stack, and then it's going to jump to the stack and start executing there. So basically, we could just specify OXD bytes as shellcode, and then it's going to start executing. And so the idea is that we're going to make a very small payload that somehow spawns a shell. It is possible to do that. According to the challenge author, that was the intended solution. Instead, what I ended up doing was I did 2 payloads. First, I send a small snippet of shellcode, which just gives us a larger read, and then I send in the real shellcode. To see what that looks like, this is just generic stuff. We connect, we set the architecture. So stage 1, like I said, I'm just going to set it up. The first bunch of shellcode is just going to allow us to do a larger read so that we can send in more shellcode the next time. Because OXD bytes, it's probably possible, but let's just make it easy and we'll ask for 100 bytes. So to do that, you just need to get all the registers set up to do a larger read. So we clear EBX, so that's the file descriptor. We're going to push 3 and then pop 3 into EAX, and so that's the syscall 3 read. We're going to push 100 and then pop 100 into EDX. And that'll give us 100 bytes, and then we do the syscall int OX80. The reason people do push and pop is because it's very short shellcode. If you do a move, some of those instructions can be pretty long. So once we do this, basically then the process is going to ask us for 100 bytes, and it's going to execute that shellcode. It's a little bit tricky. I'm copying the shellcode over into the stack pointer, and we're technically already executing, a couple of bytes into the stack pointer. And so when you run this, you just need to make sure your shellcode's kind of aligned. So really I'm at like ESP plus like 10 or something like that is where I'm currently executing. And so when I do the next read, I need to make sure that, I push my shellcode off a little bit. And I kind of do that with a little NOP sled thing here. So then we have the second stage. So we send that and everything's good. For the second stage, we're actually going to spawn a shell. And to do that, we're just going to call the execve shellcode syscall. And so first I send in a bunch of NOPs just to kind of push everything to the side. Then we're going to load OXOB into EAX. So this is specifying we want the execve call. Then we're going to move ECX into EBX. So this is the file name. And so the file name we want is bin shell. ECX currently holds ESP, and what we're going to do is we're going to send bin shell first. And so ECX is pointing right here once it's on the stack. Now EBX is going to have it, and then we're going to clear out ECX and EDX because that is the argv and MP pointers, and we just want them to be null. And after that, we just call the interrupt syscall, and it should just spawn shell. I was having some issue first. I don't know if it was a timing issue or what, but just putting in a whole bunch of NOPs ended up solving it. It would work locally without them, but once I did it on remote, it wasn't. But putting in a bunch of NOPs for some reason solved the challenge. So if you're running into that issue, the NOPs helped. Yeah, we send it over, bin shell, and we should just get the shell. So we can try running this. Python 3 solve. And we should be set. There we go, cat flag.text. And it says, elf golf shellcode golf all the golfing hurts my head. Fun. This is Pwn Cosmic Ray v2, also by Wrench. It says, woo, it's back and better than ever. This time I figured I should stop letting y'all write reviews. Too many people hurt my feelings. Sad face. We're given a netcat port and a download file. This is probably my favorite challenge from the CTF. I thought it was just a fun concept. So the idea is that Cosmic Rays, if you do hard drives or memory, sometimes you have error correcting codes because every once in a while you'll get a Cosmic Ray and it could hit your hard drive or your memory and flip a random bit. And so in this challenge, we are the Cosmic Ray, so we get to flip a random bit somewhere in the process. The idea is somehow by flipping a single bit, and the binary has a whole bunch of protections on, so somehow by flipping a random bit, we need a very specific bit, we need to be able to get, shell or flag or something. So pretty fun idea. If we take a look at the source code, it's a very simple program. It's going to set some buffering. It's going to do this Cosmic Ray, where it's going to ask us for a byte. Then we specify a bit, and we flip it, and we're done. I don't think it's possible to do this in a single bit flip. I was thinking maybe at first, the global offset table entries, maybe there's one that's very similar to a one gadget that's just off by a bit. We can flip one of those and just get very lucky. I don't think that was the case. I didn't look too hard, but just kind of comparing them, none of them look too similar. So I think we do need to have multiple bit flips to be able to solve this. So step one was figure out a way to do multiple bit flips. The way I ended up doing this was within the bit writing code, the Cosmic Ray, there's this JZ assembly call. So it's jump if 0, and this is part of the canary check. So normally this will be called, or this jump will happen. So it's not going to call stack check fail. It's just going to go to leave ret at the end of the function. But the way this code works is 74 is the opcode, and 05 is the number of bytes it's going to jump if 0. So we could bit flip this 05, so instead it jumps further than 5. So it could jump like 17 or 40 or whatever the bit flip permutations are. And if it was to jump further, we can see it's going to jump back into main. So if it jumped back into main, it's possible we could jump before this Cosmic Ray call, and it will be able to just like at the end of the function, instead of returning, it'll just jump back here and call Cosmic Ray again. And it'll just do that over and over and over so that we can flip as many bits as we want. That ended up working. I forget where it exactly jumps, but it jumps like somewhere over here or something like that. And so that way we're able to call Cosmic Ray as many times as we want and flip as many bits. From that, this point, the challenge is a little bit easier. At first I was trying to overwrite global offset table entries with the one gadget, but I was getting into stack alignment issues, so I ended up just writing shellcode somewhere in the process and then jumping to that shellcode when I was ready. The jumping code that I used was exit is called if you specify an invalid bit. So obviously bits from like 0 to 7 or 1 to 8 or something like that. If you specify a bit of 9, which doesn't belong in a byte, it'll instead call exit. So I write out all my shellcode, and then I overwrite the address where the global offset table entry for exit with my shellcode address. And so when I'm ready, I just jump there, and that's it. So really not too bad. So step one, this is the solution code. Step one, there's that jump 0 thing. So we need to change it. Instead of having a value of 5, we're going to give it a value of like 17 or 30 or something like that. And that ends up being bitflip 4. There's a couple of them that jump right before Cosmic Ray. But the issue is it kind of jumps into the middle of an opcode. And so sometimes if you jump into the middle of an opcode, it's still valid assembly. Sometimes it's not. The only one that worked for me was 4. And I think it splices one of those opcodes, and instead you get like a move EBP, ESP, or some kind of weird assembly instruction. Thankfully, it doesn't break anything and it works. I wrote a function for clearing a byte. Basically, what this is going to do is it's just going to take an address and it's just going to flip all the bits to 0 if they're set. I do this just to keep things simple because this way I can go back and check afterwards to make sure it's actually all zeroed, and it just made it simple for me. Then I have write byte. Basically, this is just going to go through and it's going to take a address and a value and it's going to write that byte there. It only works if the value has already been zeroed out, which is why I have those two functions. Then we're going to pick a random place to put shellcode. I ended up doing it here. So let's go there. Deregister TM clones. This code isn't being called, currently in execution, so I just started writing my shellcode here. We could have picked anywhere. And then the shellcode I used is just some generic shellcode from Pwn tools. Like I said, so from there, we're just going to go through shellcode byte by byte. We're going to clear the byte where it's writing the shellcode, then we're going to write the shellcode. Once we've written all the shellcode, we're going to take the global offset table entry for exit, and we're going to clear the global offset table entry, and then we're going to write our shellcode address to that global offset table entry, and then we're going to call exit by specifying an invalid bit, and that should be it. So we can try running it. We need to write like quite a few hundred bits, so it definitely takes a second. And there we go, we have shell, so we can cut out flag.txt. And it says, me when compiling with Canary is more vulnerable than compiling without. I'm guessing this is talking about the jump instruction that we used, but maybe there's a different solution. So pretty fun. This is Pwn LLM-Wrapper by 0day-t. It says, wow, I found this cool LLM wrapper for my new API. It's still in development, but they're all the hype now, so I'm sure that's fine. Give it a netcat port and a download file. So this was some code written in C. Which doesn't always look the best in Ghidra. If anyone knows how to clean this up in Ghidra, that'd be much appreciated. But basically what's going to happen is it's going to ask us for an API token, and then we get to specify a prompt, and then it pretends to like send it to some language model, but not really, it just gives us some generic output, and somehow we need to break it and get shell. The vulnerability in this challenge was on the update prompt, so you can change what you're asking it, and we'll see that it's going to read into a C string. So normally most of this is using basic strings, I think, but at some point when we update the prompt, it's going to use C string, and then we have a buffer overflow because the C string is going to have a specific size and we're able to write over the bounds. And that's the vulnerability, so we're going to be exploiting, different C string types, which is kind of fun, or the basic string type. To see what this actually looks like, let's run it. This is how I solved it. I'm only gonna look at GDB just for a quick second, and then we'll jump out and I'll show you what the stack actually looks like. But basically, we're going to be doing some buffer overflows on the stack to leak a canary, get some info leaks, and then overwrite the return with a 1 gadget. So it says, before we chat, please enter your view source LLM API token. So 1, 2, 3, 4, 5, 6, 7, 8. So I just send all A's. Then we can update a prompt. So update prompt, I'm gonna do 2. 1, 2, 3, 4, 5, 6, 7, 8. So I'm just doing A's and B's so that we can then, within Pwn debug, search for them. So I do search 1, 2, 3, 4, 5, 6, 7, 8. So we search for A's, and we can see the A's exist on the stack. And if we search for B's, we can see it's also on the heap. This is just a standard in buffering, I think. We can see that these are also on the stack. So what we have to look at is this. So this is where the B's are. We're able to update the prompt as many times as we want. And there's a buffer overflow when we update the prompt. And so right now it's all B's, these B's right here, but we're actually able to overflow and continue writing. Let me actually do 40. So these are the B's, and we have a buffer overflow here, and we can continue writing. And so the way this works is we just need to look for juicy targets. Oh, and we can also, when we run the prompt, it'll print out the values of both the prompt and the token we specified. The way and it's using basic strings. The way basic strings are laid out in memory, as far as I can tell from just playing with it in GDB, is it is the address of where the C string is, the length, and then the actual C string. So it's like those 3 fields all together. I'm guessing the address, the C string doesn't actually need to be right below. It just happens to be in this case. Maybe if it was very large, it'd go on the heap, or if you resize it, the address is somewhere else. But for this specific case, we're going to have, let me actually do -10 OX. So this is the C string. This is one C string. So it has the address to where the string actually starts. So it starts at E520, which is right here. So, this is all of our A's, or B's. This is the size. So it is 8 bytes long, which is right here. And that's it. I don't know if this is related to it. I don't think so. I think this is just something else. So we have one C string here, and then we have another one here. So we can see it's pointing to 540. 540 has a size of 8, and here are all of our A's. So we have our B's and our A's, and we're able to change these B's, and we have a buffer overflow in the B's. So what we can do is we can overflow this and put an arbitrary address in here, and if we do that, it's going to print out whatever address is here. So instead of printing out these these A's, it'll print out, if we change this to a global offset table entry, it'll leak the global offset table entry as an example. What I ended up doing is I actually just overwrite this very last byte, and I just kind of dump all of this memory looking for the A's so that I can just kind of leak the address that way, because I just want stack leaks actually. So first thing I'm going to do is I'm going to overwrite all of this, and then just this last single byte with zeros. And so it's going to print out these values up here, which I guess there's another basic string in here. So it's going to print out these values, and I'm going to be like, okay, sure, whatever. I'm going to keep, so then I'm going to do 10. It's going to print out these values, and then 18, and then 20, and 28, until I find all my A's. Once I find my A's, I know the very last byte, so that'll be 40, of where my A's live. Then I'm going to subtract 10, so I'm going to go to 30, and I'm going to leak this address. Again, I'm changing this value to leak whatever I want, because whenever I click run prompt, it'll print the current pointer, string pointer here. Once I do that, I leak this address, and when I have this address, we can start leaking everything we need. Specifically, this is kind of confusing, so I kind of wrote it out. It's probably not that much cleaner, but this is what the stack looks like. We're specifically going to be leaking, let me get these going. This is our overflow, so we're going to overflow all of this. We're going to start writing the last byte here so we can leak values. Eventually, we're going to leak this address. Once we have this address leaked, we're going to put in the address of the canary, because there is a stack canary somewhere in there. So this address is going to be the canary address, and we just know that because of relative offsetting. So canary, I think, is like plus OX80 or something like that. We're going to leak the canary value just as a string. Then we're going to do a large buffer overflow where we overwrite all of this stuff all the way to the ret, and we're going to overwrite the ret with a 1 gadget. So hopefully that made sense. Looking at the solution code, this is what it looks like. First, we're going to set all A's. Cool. So that's going to be our key. Then we're going to set our prompt to all B's. From here, we're going to start leaking offsets. And so what we do is we send C's, we say we want to update the prompt. I send a whole bunch of C's, 16 of them, and then I overwrite the very last byte with that address, so that it's just going to leak any value from 0 to 256. So like I said, I'm just going to be setting these last bytes so that I leak each one of these individually, and it's just going to leak 8 bytes at a time. So I leak that until I find all A's. Once I find all A's, I know I have found the prompt key, which is good. And from there, I can calculate, once I know where this address is, I can calculate the relative offset. Like this is the canary. Somewhere down here here's the return address, I think. Actually, I think this one's the return address. But it's just, they're all at known offsets from that address. So once I find that address, like I said, I just start leaking from known addresses. So the prompt address is at whatever our leak address was, minus 10. So we found all A's. So we know what this prompt is. It's going to be 40. And so then minus 10 would be this address. So this is the address of our prompt. Then we found the canary string. It is over here. So it is whatever leak value we found plus 18 in hex, which is right here. And then we also leak libc. Oh, we needed libc for something. I think if you go down, eventually you find a libc address. So I leak out libc. It's plus 88. Cool. So we did mangle a bunch of stuff. Like we mangled this address when we were doing our buffer overflows, and this address. We need to demangle everything. And so the very last step is, while we're writing our 1 gadget to the return address, just doing a standard buffer overflow, we just need to make sure we kind of demangle everything and put it back into the state it was. So it started out with B's. Basically what I do is right at the start of the program, I just take a screenshot of this. And at the very end, after I'm done mangling, I see what the differences are. So this prompt address, this one is 20 minus our address. So we can see it ends in a 2700. And right now our current leak address is 20. So we just subtract 20 and we'll get the address that is supposed to be here. Once you start playing with it, it's really not too bad. So then we just, update all the values. This had a prompt address plus 10, then it had a value of 8, then it was all A's, and then 0. Like I said, we're just going through and we're just making sure all the values are what they should be, because we're going to do a huge overwrite, including like the canary, some other stuff, and then eventually the return address. So once we've done all that stuff and we call exit, it'll go through the return, it'll do the canary check, but thankfully we copied over the canary and we overwrite it, so it's all set, and it'll eventually call the one gadget. And once the one gadget is called, we win. So Python 3. This one, it takes a couple times to run. Sometimes if the offset is too high, it's not going to work. So hopefully it works. But we can see these are the values are leaking. So it's leaking addresses, it'll leak some C's, it leaked a size, some more C's, another pointer. This one might be too high. I think I'm going to have to redo it. Yeah. Because one of the values I leak is like current value plus 80, it doesn't wrap over. I could make the code more reliable. I'm just lazy. I think this one's too high too. I think this one might be good. It'll be close. So we found all the A's. So we found the hex prompt, the canary, the libc leak, and then we should be good. Yeah, so then we overwrite. This is that final payload we send. And so this is like resetting the stack all into correct values. So we can see we got our B's and our A's, some libc sort of value. And then this is our one gadget. And here's the canary too. So we set the stack into a nice clean state. Then we call exit and we get the flag. So cat flag.text. Oh no, it died. I should have printed out the flag when I have a chance. There we go. And it says vsCTF, an LLM definitely wrote that code. So fun. This is misc reCAPTCHA v39 by Sahwang. It says, I was browsing the web and happened to see a website that uses reCAPTCHA v39. I tried to solve it but failed. Can you help me out? Surely it's much harder than v3. So if we go to the website, it says, find the area of the shaded region in the square whose side length is 10. The absolute area of your calculation needs to be smaller than 1. You have 5 seconds to answer each question, blah, blah, blah. So we're given this image, and we need to calculate the area of this shape. So pretty interesting CAPTCHA challenge. If we view the page source, if you read over this really quickly, you'll find out it's just working over WebSockets. It's going to say like start to the WebSocket, and then it's going to read in some text, and then it's going to read in these PNGs. And from there, you just do that 100 times, and if you get 100 correct, it'll give you the flag. So to solve this, I just wrote a little WebSocket, some WebSocket code in Python. So I take that WebSocket address, and you can find it from the code or just from the network tab in Chrome. When we send it to 0, that means start. And then while true, it's going to receive the message. The message just says like how many you have correct or wrong. Then the next message that you receive is the image. So this is just a PNG image. So I save it as captcha.png. Then I use some Python image library called PIL. I load it in. I get all the pixels. Then for the pixels, if they are white, the code is 240, 240, 240. I just printed out the pixels and you can see that. If they're non-white, they're not going to be equal to 240, 240, 240. So I just count all the white pixels, and then from there, or I count all the non-white pixels, and then from there I just calculate the ratio and I send that back. And that was it. So if we run it, like I said, it'll go through 100 of them. Cool. And at the very end, you get the flag. It says, vsCTF, would you rather pay it to solve it? This is reverse exorial by Neil. It says, are you being exorial with me right now? Or exorial? And we're given the download file. So this was a interesting reverse challenge. And so what's going to happen in this reverse challenge is it's going to do a bunch of XOR operations, and we need to guess the flag, and if we get it correct, it lets us know. There's a bunch of anti-debug checks, so we can see that this is main. If we go through, we can see it's going to check some p-tracing, so it doesn't like debuggers. There's also some code in here. This will check to see, oh, no, that's an error message. Where's main? There's some code, I think it's this one. Yeah, there's some code in here that'll check like what the running process name is, the command line, and if it sees like GDB or some other tools, it'll also exit out. So there's a bunch of anti-debug measures, but eventually if you go back to main, it'll ask you what the flag is, and it'll do a bunch of comparisons, and if you get it correct, it'll let you know that you got it correct. And you can see it does some like length checks and stuff like this. I think this is the win function, but we can check that in a second. So first step first, I tried to get this working in GDB, and I was able to, though I didn't end up being that useful though. But if you want to get it working in GDB, what you can do is just kind of modify the assembly so that it works. So you can take these compare calls, so like it'll jump if not 0, if you're only going to be loading it in GDB, or if you want a version you can just load in GDB, you can just patch the, oops, not that. You can do patch instruction in Ghidra, or any of the, oops, did that twice. Patch instruction. So instead of jump not 0, you can do jump 0. And so I just made a couple of these different changes, one here and then one for when it checks to see if it's GDB. And then that way, and then you save that new version if you save it. And so then when you can load it in GDB. And so I saved it as xorial.1, and now we can run it in GDB and it won't just instantly crash. So we can see pass me the flag. From there, I played with a couple different functions. There's different functions that print stuff out. Like these void functions. I'm just guessing this is win. I mean, I know it is win, but it's to do all these XOR stuff, and I don't really feel like doing it myself. So what you can do is you can copy this. Actually, we need to do VM map, and what we're going to do is find the start. So this is the start of the code. We're going to do jump here plus this code. So we're going to jump to, come on, I don't know why my mouse is being so weird right now. Right here, and I think we need to wrap it, and this is an OX. Jump. Cool. So we jumped to this function just to see what it prints, and it says, woot woot, you got the flag. And since it says woot woot, you got the flag, we know that this is the win function, and this is what we're aiming for, or to get to that code. And so if we go back to main, we know where win is. And so we have to pass all of these checks. There's a bunch of stuff in here, but I'm pretty lazy, so I didn't do any of that. Once I know there is a win function and it's just a bunch of XORing, I basically pass the code off to Anger. So this is the win condition right here. So I just copy this address out, and we're going to send this to an Anger script. If you're not familiar with Anger, it's absolute magic. It's like a symbolic execution engine that'll solve CTF challenges for you. Specifically these reversing type challenges. And so this is what Anger code looks like. I'm going to load in the binary. I'm going to set a state. So like, yeah, just an entry state. I'm going to say this is the address I'm looking for. So what it's going to do is Anger is going to try to symbolically find a way to get to this address. And this is that win address we just copied out. I put in a couple of void addresses. These are just like functions I know that are failure, and so that way Anger doesn't spend too much time going through them. You just kind of like find some addresses, like this exit call is probably bad. So 1B 4A, and I mean you can jump right before that too. So 1B40. I don't even have that in here, but you can put it in here, and so it just saves a little bit of time. And then from there, Anger will just figure out the input that gets you to that location. And under the hood, like I said, it's symbolic execution. It's using Z3, very powerful stuff. So we can run this, Python 3, solve.py. It does take a couple of minutes, but it's just going to start calculating stuff, and eventually, hopefully, it finds the flag for us. And we get the flag. It says, weak anti-debuggers are no match for the elite. So, fun. This is Web Optmized-admin bot by Jaden. It says, launching a whole instance of Chromium for basic client-side challenges is too archaic and uselessly resource-intensive. Check out my Optmized-admin bot. We're given a challenge journal link and a download file. So pretty simple challenge, but pretty fun. The idea is, so this is the server code that's running. It's going to have some visit code, and so normally this would spawn like Puppeteer or something like that, and so you would be launching a full Chrome instance, but like they said, they're going to do some JS DOM library, and so what this code does is it'll take in some HTML and it'll run the JavaScript on that HTML, and it's just like a virtual DOM that you can play with. So they're going to be rendering this stuff. What makes this fun is this JS DOM execution also kind of runs in the Node.js context of this server, and so when you're running JavaScript in Node.js, you can do stuff like exec sync and spawn stuff and run shell commands. So it's possible that maybe an XSS, while rendering this JS DOM, would allow us to get shell execution within the Node.js environment. And if you read the docs for JS DOM, it says that this is possible. They didn't give any good examples, but they said most likely if you do run scripts dangerously, it is most likely there's a sandbox escape such that you can execute this code. At first, the code also didn't have this virtual console send to console, virtual console. This wasn't there. I added that just so I can get some debugging. Otherwise, you can't see the output and the errors from this JS DOM code. And that was the challenge. So from here, we somehow have to figure out how we can escape this like JS DOM sandbox and start executing Node.js code and get shell. To do this, instead of like going through the server and passing URLs and stuff, I wrote this little solve.js script to just kind of quickly iterate, because I tried a whole bunch of different ideas to get this working, and eventually did find something. So it's not too hard to find a process. So this is normally how the Node.js kind of sandbox escapes look like. You're going to do something like this: some window, global object, constructor, return process. And from here, normally what would happen is you would do like, I think it's process.main module, and then you can do require and child process, stuff like this. Something like this. But main module wasn't there, and I also couldn't find a reference to require. I'm not really sure why, but because I was looking through the JS DOM code and I didn't see anything that was like removing main module, so I'm not really sure. But if you play with the process object, eventually you'll see another interesting thing called binding. That does exist on this processing object. And so doing some research, this binding function was pretty much the whole idea behind the exploit. This is going to load the C code for specific libraries. And so this is what Node.js is using under the hood. And so there's a whole bunch of them for like operating system and file systems and just any C code that is binded into the JavaScript runtime. And there's one called spawn sync. And so this allows us to call spawn synchronously. The spawn sync code is kind of really weird. You can't just call it with like some arguments. There's like a whole bunch of weird stuff you need to do. Eventually I found someone else has used this exploit before, and basically they went through the child process function and found these functions that worked. And as long as you call these, it'll put everything in the correct order so that we can actually call this spawn sync. So this is someone else's code I copied from online, and they copied it from the child process library. But using this, eventually you're able to call spawn, spawn sync. But once we're there, we can do bash. I was trying to copy it out and send it somewhere, but they're like XML implementation and they don't have fetch, and it wasn't loading images. I had a hard time like just getting it to like send the flag to my endpoint. So instead I just did bash. I sent in the arguments, run command. You have to do the read flag command because the file is owned by root. The flag file is owned by root. But I just copy the output of the flag into index.html, and so that way the next time I view the page, it'll just be the flag. So basically the whole idea behind the exploit was process.binding spawn sync. This was the solution. I'm curious if other people had different solutions. Maybe somehow you could get to main module. I am very curious. But to actually run this, we have to do a couple different things. So first let's go into dist. Python m simple http server. Then we're going to load another one, and we're going to do ngrok, I think it's 8000. HTTP 8000? Yep. So we load this, and we're going to go to exploit.html. Cool. We're going to start this instance. We're going to wait for it to load. Cool. We're going to give it a URL to visit. It's going to visit it, and if it worked correctly, when we come back, it didn't work. Let's try that again. Let's make sure this is live. Exploit.html. Oh, I spelled it wrong. Maybe that's why it was never working. It has visited your webpage. Now if we go back, and there we go. vsCTF should have just used Puppeteer, so fun little challenge. And that was all the challenges I was able to solve. Like I said, overall, very fun CTF. Had a lot of fun. I wish it was a little bit longer so I could play with some of the other challenges, but it is what it is. I'm excited to see some write-ups from other people. And thanks again, ViewSource, for hosting, and I will see you at the next one. Cheers.